a tough time slot before lunch with science in the title, but thanks for showing up. Quick show of hands. Who's growing cannabis? Excellent. Who's testing cannabis in-house? Who would like to grow better, cleaner cannabis? Okay, so what we're going to chat about today are some maybe non-traditional approaches to bringing in-house some quality control or some visibility on how your crop's doing, or actually your extraction is doing. And I'll break this down into a couple different sections. There is going to be some science referenced in this deck, but it's designed to be high level, and the end solution for your lab or your cultivation is designed to not need a scientist to do. So if you have any questions, just feel free to clarify those at the end. But a brief introduction, followed by an intro into using FTIR to look at the cannabinoids in cannabis flower. Following that, we're going to actually look at the terpene profile of the same sample. And following that, we're actually going to look at the decarboxylation reaction often found in the extraction processing environment. For those that don't know PerkinElmer, we are not a testing lab. We are a technology company. It's a US-based company. We're global, 11,000 people, 87 years old, with a strong corporate support for medicinal and recreational cannabis where it's legal. I've been working for them for the last 8 years on the West Coast, Canada, California, Washington. I'm now based in Vancouver, but cover the world. I work in the food group, so we see a lot of similarities from the challenges we've seen in food, now in cannabis. Vice versa, we see some emerging market needs in cannabis that we can use elsewhere, but we're excited to address the science around those challenges. So for me, it really comes down to the chemistry of the plant. I'm not going to focus on calling cannabis cannabis or hemp hemp when the chemistry really dictates what that might be. For all intents and purposes, we know that the federal requirements of less than 0.3% deem it to be hemp. But what we're more comfortable maybe looking at is the ratio of cannabinoids in that plant. And I'll be using type 1, type 2, type 3 chemovar references in this talk. Obviously, 1 being THC dominant, 2 being a 50-50 approximate mix of CBD and THC, and then third, a CBD predominant plant. And we know cannabis is extremely complex in how it's made up. There's a lot of organic components in that flower, in that stem, in that stalk, which are exciting, yet sometimes quite challenging to the laboratory technician or cultivator because they'll interfere or they'll influence the desired outcome. A lot of focus obviously is on the cannabinoids. We've quantified over 120 of them in flowers. Yes, not all to the same concentration. Some are very, very trace level. But there's a lot of cannabinoids in there. Today we're going to focus more on the dominant THC, CBD, but you can apply these techniques to all of the other cannabinoids that you maybe want to study. I'm also going to chat about terpenes, as I mentioned, and also appreciate that there are other constituents in the flower, such as waxes and oils, that can interfere in your process. So understanding that at the same time is hopefully of value. So as I mentioned, we're not a testing lab. We are a partner that you can work with in any stage of your cultivation or your manufacturing process. Here we see the life cycle for a cannabis plant, an outdoor cultivation site, following harvesting and trimming, followed by an extraction of some kind, maybe then some further purification or distillation. And then if it's for the edible market, we're seeing that being incorporated into a non-cannabinoid raw material before it goes to market and potentially before it's tested. So when I bring up chemistry in California in particular, a lot of people kind of eyes go wide because it's a lot of chemistry to take in. And then what we're looking at here is the regulatory requirement for the chemistry testing in California. So this is broken down into cannabinoids, terpenes, residual solvents, heavy metals, mycotoxins, and pesticides. So this is what we do very frequently with our third-party testing labs. There's a lot of options for those labs to do this efficiently and economically. That's not the focus of today's talk. What I'd like to talk about is things you can bring in-house to offer more quality control so that maybe when you get to the point of testing before you go to market, you have more confidence in that's what your product's going to have in it. So I'm going to start by using a very, very mature technique. For those of you that did any chemistry in college or university, one of the first experiments you might have done might have been with an FTIR spectrometer or an IR spectrometer. That's using infrared radiation to go through a sample. When you shine energy at a sample, it's going to absorb and interact with that sample, and that sample signature is what we can use to identify chemical species in that sample. FTIR is used extensively throughout the world in all markets and applications: food, pharma, nutra, environmental, petro, cannabis, R&D, you name it. And it's a very, very cost-effective, easy tool to use. So the first thing we're going to look at is what can we do or model or test in a cultivation environment. So by saying at line, I'm referring to a technology we can bring inside your cultivation or inside your organization. I'm not saying this is going to be inside the canopy necessarily. What I'm saying is that if you could sample a piece of that flower from the canopy at that certain time, you can then test that real time in the room or in the room next door. There's no prep, there's no delay in sample turnaround time. So we're focused on looking at the cannabinoids first because we've seen a lot of customers or clients come to us. They spent hundreds of thousands of dollars retrofitting their grow with new lights, new HVAC, and they really want to know, how's the chemistry changing? And they don't want to have to send the test out repeatedly to a third-party lab when they've got hundreds of tests to do, and they're working with very tight time frames for the cultivation. So they approached us, and they said, what can we do quickly in-house? And FTIR, as you see, is a fairly small, portable technology. You can use it in the field. It can be battery-powered, but it can also be fully GMP CFR compliant. So you can use it in a number of different ways. And what we're focused on is the infrared energy region. It's not harmful at all used in an instrument like this. It's contained. It's safe, but it gives you a lot of insight into what the chemistry is doing in your sample. And why do we see differences? So if you look at any molecule, it's going to be made up of, or any organic molecule, it's going to be made up of carbon, hydrogen, oxygen, nitrogen, and those atoms are going to form a molecule, and they're going to have a bond, so they're going to be attached. And those bonds are not rigid, they move. So when we shine energy, or IR energy, at those bonds, they actually vibrate, they move, they twist, and how they twist is very indicative of what the chemistry is. So what you're seeing here is a representative spectrum from the infrared region of a cannabinoid. So you see the CHs and the OHs have different degrees of intensity at different positions. That's about as much science as I'm going to get into because there's books and books and books that you could go into. But what I'm trying to say is every cannabinoid is going to have a slightly different signature. And this signature is actually proportional to how much is there. So if you have a high THC, you're going to see a higher intensity in that spectrum. So you can actually model and predict what an unknown flower is going to have once you've qualified your model prior. And how do we do this for flower? So this is a non-destructive test. And what I mean by non-destructive is you could literally take this sample off the instrument and smoke it or process it like you would any other flower. There's no solvents. There's no real prep other than maybe homogenizing that flower. And we can see that on the top of the instrument here. What you do is you place that sample, it's about a gram and a half, into a Petri dish that spins. And by spinning, you collect thousands and thousands of data points from that sample. And that average of data gives you a much higher confidence in the chemistry. But this is a very quick test. It's about 90 seconds. So you could be putting multiple buds on here from different parts of the canopy, different heights of the cultivation program to see what the chemistry is at that specific point. This is getting a bit deeper into the chemistry. Basically, this looks like a very messy, similar graph, but to a spectrometrist, it tells a lot of unique information. So this is embedded into this technology. We've already done the hard work, which took us about a year to model a representative set of flower. But these small, subtle differences actually mean a big difference in the final insight. And we can see just briefly the blue curve is the first derivative of that previous slide. and the red CBD signal are actually quite different. So once you recognize that there are these differences, you can then model appropriately your cannabinoid concentration in the flower. So again, this is a fairly straightforward workflow. As I mentioned, we've done a lot of the prep to prepare a reference model set. So what I mean by that is we have to go and correlate to a initial test. And what we see a lot of people using for the cannabinoids is HPLC. So what we've done here is we've worked with a number of cultivators, growers, and extractors to get a representative sample of their typical kind of product. And that for THC, for example, is very, very low to about mid-20s, 26%. Take a sample, we grind it, run it, and then we use a reference HPLC number. So what we do is we build this model. So we know that if we take this chemovar, run it, we get this signal. What that allows us to do is then run the unknown. So we believe we have a very good starting point for all chemovars right now in California or the US. If you have a very, very unique strain, you might want to include a few extra points, but that's usually done in the introduction training and can take a couple days, but not longer than that. And what this gives you is basically instant information on, sorry, let me back up. This is what we use to make that model, over 300 samples, 50 cultivars, concentration ranges of about 0 to 24, 0 to 22. My apologies, not as high as I thought, but we could go higher. It's just we had limits of the cannabinoid concentration from those samples. But we can see that the data is a very nice distribution, so we're not focused on just high or just low. We tried to get everything to make this as useful to you in the field. And this is the CBD, so we're happy with those linearity. And the end result is an SOP or an instrument that you can plug in and run cannabis. And we've had a lot of success in California in particular. We've had a lot of success in Canada in the indoor grows. But this is where we're excited to basically release this capability to cultivators and show them the small changes in their cultivation program and how that changes the chemistry. So this is kind of a starting point for people wanting to bring in-house analytics. I'm not saying this is going to replace third-party testing. It's going to help you support your third-party testing program. And on the same sample, what we're seeing is a lot of interest is also of the terpene profile of that flower. A lot of claims, a lot of marketing, a lot of branding out there is now being pivoted over to the terpene, particularly because of the entourage discussion. So to go into that, you really need to know the science of that flower or that plant, and terpenes are kind of second in line for adding value. So what we looked at, and we took this model from the brewing industry. So the brewing industry has used this technique for decades to look at their hop profiles, their beer profiles. And let's just say brewers are pretty straightforward guys and girls. They don't like to do science. They want to press a button. They want to get a number and be happy or sad. But that's really what we were able to leverage from doing that for years and years, having a low-cost, easy-to-use system, but now we can adopt it to look at the terpenes in cannabis. As most of you know, there's a very strong similarity between hop terpenes and cannabis terpenes, but they obviously differ to some degree. So what we're looking at on the left is the terpenes. This is the California list. There's hundreds and hundreds of terpenes out there. We can look at any terpene you want to. Right now, this references, I think, the 39 California wants you to see. Residual solvents can also be done on this system. I'm not going to get into those today, but if you are an extractor wanting to test your product before it goes out for third-party testing or to make sure you remove that solvent, this same system would do residual solvents. And as I mentioned, we need to make it simple. So what you do is you take that sample maybe you had on that near-infrared Petri dish that was spinning for your cannabinoid concentration. You take that and you place it into one of these glass vials and you cap it. And that capped vial basically sits in this carousel and you press go. You walk away. And what happens, we apply heat to the vial, and if you have a solid, liquid, powder extract in the vial and you heat it, the volatiles, and we know terpenes are volatiles, get released and they situate in the headspace, which is the gaseous component above the sample. That's why it's called headspace gas chromatography. But what this allows you to do is take a syringe needle and just sample that gas. You're not pulling out any of the cannabinoids that are not they're going to be in the solid, or any of the waxes or the other pieces that aren't volatile. So what it means is you get a very clean sample point. So that means low maintenance on the instrument, very good sensitivity. If you want to look down to parts per million, parts per billion terpene levels, you can. So again, but we design it to be very straightforward, so you don't have to be a scientist necessarily to run this. And why do we see a lot of uptake in bringing the terpene testing in-house? I like to reference these two slides from a collaborator we have up in Santa Cruz. And they test a lot of the Emerald Cup winners. And what they did, they took the study of the aggregates of the winners and the mean. And they looked at first the cannabinoid differences. So this is looking at the difference in cannabinoids between the winners and the mean. And we see that they're very, very similar. So the winners that year weren't differentiated by having a higher cannabinoid product. What they were different by a significant amount, is the terpene profile. So now we're seeing a lot of people now want to really understand what their terpene profile is of their flower or their product so that they can be confident in replicating it and being different in the marketplace. And this technique gives them that capability. And as I mentioned, this is a pretty quick, straightforward test now. It took some time to get it to this point, but we're comfortable to doing 38 in about 8 minutes. So this is more towards like a high throughput lab where sample throughput is key. If you're an in-house quality control lab, you maybe have 10, 20 samples a week. You're not as focused as the time it takes to get through the system, but now know it can be as quick as 8 minutes. So this is looking at 38 terpenes. We can obviously extend this to look at more if you have a particular chemobar with a particular terpene that's not included. So we're switching gears, leaving the flower cultivation world. Any extractors in the room by any chance? Couple? Okay. So everything I've talked about also has the same kind of value in the extraction space. So if you're making an ethanol, a CO2, a water, a pressure product, it's the same chemistry that's going to have the same value in the end market. So understanding it throughout that process is key. The one thing we saw a lot of challenges around and not a lot of knowledge was the straightforward decarboxylation reaction. So a lot of people producing an edible where they're decarbing their product, whether it be before or post extraction, did not have a good understanding on how well they did that reaction. What we seemed to see was most people putting their product in a heating vessel, turning it on, and almost walking away until they thought it was finished. We have references where people would turn the oil onto a hot plate, watch the CO2 bubbles dissipate, and then turn it off. Their beautiful golden oil would turn into this black sticky mess. And they thought the same starting chemistry point would be the same ending chemistry point. That's definitely not the case, depending on the conditions, because oxygen, heat are going to create some very interesting chemistry changes in your product. So we were asked to put together something very simple to understand when that THCA converts to THC and then stop the reaction at that point, not let it extend and cause any degradation. We focused on THCA to THC, but you can do CBDA to CBD. You can do any decarboxylation reaction. But specifically, we're looking at this reaction here. So we're taking off this carboxylic acid compound, which when we apply heat, we know gets kicked off to CO2 and then replaced by a proton here for THC. So how we did this is we looked at the industry. A lot of people doing hot plates, a lot of people doing ovens, some doing it before extraction, after extraction, but no one really having a good understanding of when it's complete. And we looked at it, again, using FTIR. So you'll notice some slight differences to the system I showed you earlier. This is because this is a mid-infrared. And what I mean by mid, it's a slightly different energy range. This actually gives you a bit more information of your sample, and it's exclusively used in the oil, natural product world because of how much chemistry you can learn from just one spectrum. So for cannabis oil, you need literally a couple milligrams. There's a 1 millimeter crystal sitting on the top of this stainless steel plate. And that's all you need to cover to get a strong, strong signal. So what you can do is you can just sample from your decarboxylation reaction vessel, if you can access it, and just sample the oil as that reaction monitors, which is what we did for a traditional THCA to THC hot plate overhead stirrer decarb reaction. And again, looking at this high level, it might look quite similar, but what we see is there are subtle changes. And these subtle changes, like the previous model, can be recognized and modeled to give you a predictive tool for future extractions. So here, this is where the OH and the carboxylic acid is present in the spectrum. So any changes around that area, you know you're changing parts of that molecule's molecular chemistry. So we use this signal to model THCA to THC. And we did this work very quickly. Compared to the flower method, which took months to get that many samples of flower from that many different cultivators and chemovars, this was done in about a week. So what this was able to do was give that extractor a very nice quality control tool to use after only really a week's worth of work. And what we did is we basically monitored that reaction over, I think it was over 15 minutes, and we then ran that oil with the traditional HPLC assay to tell me the cannabinoid concentration. And then we ran that same sample at that same time point on that FTIR. And we can build that model, or that aggregate model set. And what you're seeing now is the actual measured and then the predicted model we get from that work. So now moving forward, that extractor can just sample that oil, place it on the FTIR, and get a number back. And the difference you can see is significant. So we're down from 75% in that oil down to, I think, 50-something here. And what I'm not going to show today is that we actually looked at the byproducts. So even after 80 minutes, the byproducts in that oil were significant. So they lost some of the minor cannabinoids. They were losing them out completely. So this was a medicinal product with CBDV in it, which was being basically destroyed in this process. So there's a lot of insightful information, but the core value was to monitor that THC. And we did that with some good linearity. So we're very confident in putting this in an extraction environment to monitor this reaction. Extracts as well. And that's really kind of the summary of that work. As I wrap up, the idea is to make this as seamless and straightforward as possible. We heard earlier that the markets differ significantly when it comes to the chemistry or the testing, depending on where you are. But what we recognize that in-house quality control is going to have similar needs in all those spaces. So what we've developed is an SOP. So it comes with a recipe or an instruction or a manual to really allow you to get working faster and have the highest kind of turnaround on that investment. And this is with all our technologies, but to my points earlier, the FTIR and the GC are ready to go. And we put our methods through what one of the industry's kind of most recognized proficiency tests is. So we participated in the Emerald Scientific PT test last year, and we were awarded our badges successfully. So we know that when we take in an unknown, like the PT study offers, we get the right number for the test. So in summary, hopefully I've shown a couple options that are maybe more attainable, approachable, and valuable for a cultivator or an extractor to bring in-house. That's just the tip of the iceberg of what we can do or help a cultivator with, but hopefully it's a starting point. We see the FTIR as a non-destructive tool. You can use it very easily and quickly, and actually get quite a lot of science out of that one sample. And then GC headspace, very straightforward. Cap it, put it in the carousel, press go. Full terpene, full residual solvent profile in a matter of minutes. And to us, hemp cannabis, it's the same. It's the chemistry that's going to dictate what you have. And then lastly, we're excited to work with everybody. I cover the globe. I cover all aspects of this market, also aspects of the science. If you have a challenge, an idea, I'd love to talk to you. Feel free to reach out to me. I'll be here tonight, tomorrow. I'd love to get a better idea of kind of how we can help. And with that, that's all I have. Thank you for your attention. Enjoy lunch.